What specific problem does the Hymba model aim to address in the context of language modeling, and how does it improve upon existing architectures like transformers and state space models?
The Hymba model aims to address the efficiency challenges posed by transformers, particularly their quadratic computational cost and high memory demands, while also overcoming the limited memory recall capabilities of state space models, SSMs, like Hymba. By integrating attention heads and SSM heads within the same layer, Hymba allows for parallel processing of inputs, leveraging the high-resolution recall of attention and the efficient context summarization of SSMs. This hybrid head approach enhances the model's flexibility and expressiveness, enabling it to handle various information flows and memory access patterns more effectively. Additionally, Hymba introduces learnable meta-tokens that improve attention distribution and performance on recall-intensive tasks, further optimizing memory usage and throughput. Overall, Hymba establishes new state-of-the-art performance across various benchmarks while achieving greater efficiency compared to both traditional transformers and previous hybrid models.
How does the proposed method, Hymba, work? Illustrate step-by-step the architecture and the process of fusing attention heads and SSM heads within a layer.
Hymba integrates attention heads and state space model SSM heads within a single hybrid head module, allowing both types of heads to process the same input simultaneously. The architecture begins with an input sequence that is prepended with learnable meta-tokens, which serve as a compressed representation of world knowledge and guide attention towards relevant information. The input is then projected into queries, keys, and values for the attention heads, as well as input features and gates for the SSM heads, using a unified projection matrix. The outputs from both heads are computed. The attention heads utilize a softmax function for their outputs, while the SSM heads employ a data-controlled linear operator. Finally, the outputs from both heads are normalized and rescaled using learnable vectors, averaged, and pass through a final output projection, effectively fusing the strengths of both architectures to enhance recall and reasoning capabilities while optimizing memory efficiency.
Can you provide a simple yet illustrative example that demonstrates the interaction of attention heads and SSM heads in Hymba? Walk through the steps of the algorithm using an example input.
In the Hymba architecture, attention heads and SSM heads interact in a parallel manner to process the same input simultaneously, enhancing both recall and reasoning capabilities. For example, consider an input sequence consisting of tokens representing a short sentence, "The cat sat on the mat." When this sequence is fed into the hybrid head module, the attention heads utilize their high-resolution recall to focus on specific tokens, such as cat and mat, effectively capturing detailed relationships and context. Simultaneously, the SSM heads summarize the overall context of the sentence, maintaining a constant cache that allows them to retain the gist of the information while processing it efficiently. The algorithm begins by projecting the input sequence into query, key, and value representations for the attention heads, while also preparing the input features for the SSM heads. As the attention heads compute their outputs, they may emphasize the relationship between cat and mat, while the SSM heads provide a broader context that helps in understanding the entire sentence. Finally, the outputs from both head types are normalized and averaged, allowing Hymba to leverage the strengths of both attention and SSM mechanisms, resulting in improved performance on tasks requiring both detailed recall and efficient context summarization.
What are the theoretical or practical advantages of integrating attention and SSM heads in the Hymba architecture compared to traditional transformer architectures or previous hybrid models?
The Hymba architecture offers several theoretical and practical advantages by integrating attention and SSM heads within the same layer. Firstly, this hybrid head approach allows both heads to process the same information simultaneously, enhancing reasoning and recall accuracy, which is a significant improvement over traditional transformers that rely solely on attention mechanisms. Secondly, the integration addresses the inefficiencies of previous hybrid models that stack attention and SSM layers sequentially, which can lead to information bottlenecks. Hymba's parallel processing mitigates this issue. Additionally, the use of sliding window attention and cross-layer KV cache sharing in Hymba optimizes memory usage and throughput, achieving up to 3.8 times cache reduction and 2.7 times throughput improvement compared to traditional transformers. Finally, the introduction of learnable meta tokens enhances the model's ability to focus on relevant information, further boosting performance across various tasks, including common sense reasoning and recall-intensive tasks, thereby establishing new state-of-the-art benchmarks.
How is the effectiveness of Hymba validated? Discuss the experimental design, datasets used, benchmarking metrics, and how they substantiate the claims of performance improvements.
The effectiveness of Hymba is validated through comprehensive benchmarking against state-of-the-art SOTA small language models, LMs, and various experimental settings. The experimental design includes direct comparisons with popular small LMs, such as Llama and Smol LM, across a range of tasks, including common sense reasoning and recall-intensive tasks. Hymba models, specifically the 125M, 350M, and 1.5B parameter versions, were trained on diverse datasets, including DCLM BASELINE1, 0 and Smoln corpus with a total of 1.5T pre-training tokens. Benchmarking metrics focus on accuracy improvements, cache size reduction, and throughput efficiency, with HYMBA1, 5B achieving A1, 32% higher average accuracy than LLAMA3, 2 to 3B, while requiring 11, 67 times smaller cache size and being 3, 49 times faster. These results, along with detailed ablation studies and comparisons across different architectures, substantiate the claims of performance improvements and demonstrate Hymba's superior efficiency and effectiveness in handling various tasks.
What specific results and performance metrics were achieved by Hymba in comparison to other models? Include details about accuracy improvements, cache size reductions, and speed enhancements in your answer.
HYMBA1, 5B achieved significant performance improvements over other models, notably outperforming LLAMA3, 2 to 3B by 1.32% in average accuracy, while requiring 11, 67 times smaller cache size and being 3, 49 times faster. In comparisons with the strongest sub-2B baseline, Smol LM 2 to 1, 7B, HYMBA 1.5B demonstrated a 1.02% average accuracy improvement, A19, 91 times reduction in cache size and a 2.79 times increase in throughput. Additionally, when benchmarked against small LMs trained on no more than 2T tokens, Hymba achieved average accuracy improvements of 5.21% and 5.41% over PHI 1.5 and H2O Danube 2 to 1, 8B, respectively. The model also established new state-of-the-art performance across various tasks, showcasing its efficiency and effectiveness in both general and recall-intensive tasks. Overall, Hymba's architecture not only enhances accuracy but also optimizes memory usage and processing speed, making it a leading choice among small language models.